Hi friends, fluid mechanics as a subject plays an important role, or it has got very good weightage in all competitive exams for mechanical engineering. So coming to GATE exam, GATE mechanical, 6 to 10 marks. So the weightage is changing from year to year and set to set. So on an average 6 to 10 marks out of 100 marks, good weightage. Coming to ESC exam, we know in ESC you have prelims. So in ESC prelims mechanical, again the number of questions are varying in the recent years. Of course, on an average, you can expect 18 objective questions in the prelims of mechanical. Approximately 18 questions. 18 questions means 36 marks. Now come to mains. So in the mains exam, you will have a weightage of approximately 80 to 90 marks. And again, in various state service commissions, ISRO, various competitive exams, fluid mechanics, and of course, including hydraulic machine, it has got huge weightage. Let us see various definitions. First, the definition of a fluid. As all of you know, a fluid is a substance which is capable of flowing. A substance capable of flowing. Why it flows? Why it flows? This is a big question. Suppose there is a surface, solid surface. On this, you have some fluid. You apply shear stress. Shear stress, shear force, or tangential force. Let us say this is some tangential force. I am assuming same force, means no change in the magnitude of force with a reference to time. So with the same force, assume this is at a time t is equal to 0. Now after some time, let us say t1, it is deforming. Let us say t2, again deforming. T3, deforming. Same tangential force, but deformation is continuous. Sir, what is the magnitude of shear force which causes this fluid to flow? Whatever may be the value, even maybe the smallest shear force, the particles will move and it will have continuous deformation. So in a nutshell, a fluid is a substance which is capable of flowing, and it will have continuous deformation due to the action of tangential or shear forces. Then you may have a question. So, sir, fluid is in the state of rest. If the fluid is in the state of rest, what is the shear stress? I think most of you may be knowing. When the fluid is in the state of rest, shear force is 0. A fluid is a general term. Fluids consist of both liquids and gases, because both liquids and gases will be subjected to continuous deformation even on the application of a small force. Of course, I need not give the examples for liquids and gases. Now there is another term, vapor. So what is a vapor? In fact, vapor is a gas, but very nearer to liquid phase. For example, steam, a pure substance. Steam is a classical example of vapor. Let us see the general definition of fluid mechanics. Fluid mechanics is a science that deals with static and dynamic conditions of fluid. It is a science dealing with the static and dynamic conditions of fluid on application of forces and the interaction between this particular fluid with respect to another fluid or another solid in the boundary. So in a nutshell, fluid mechanics is a science dealing with the static and dynamic conditions of the fluid upon the application of forces and the interaction with respect to another fluid or a solid on the boundary. Let us see the difference between a solid and a fluid. Let us take a solid body. You apply a tangential force or a shear force. Assume this particular force is constant. Now this body will deform. I say this as elastic deformation. So this deformation, let us say here delta x, here also delta x. So this deformation is constant for a given force. Sir, I want to have change in deformation, means say delta x should increase, delta x should increase. I want to have more deformation. In such a case, the magnitude of the force applied should change from time to time. If you want to have continuous increased deformation, the force also should increase from time to time. In a nutshell, deformations are not continuous in case of solids for a given constant tangential or shear force. Now let us go for a fluid. Of course, I have already explained earlier. Let us see this again for more clarity. Earlier I told you, in the state of rest, 1 1 dash, 0 1 1 dash, in the state of rest. Suppose at a time t1, 2 2 dash, after some time, let us say this as 3 3 dash, let us say this as t1 t2 t3. Of course you can have so what I am trying to emphasize here, the magnitude of force here same. For same force, deformations are continuous. In the case of solid, deformations are not continuous as long as the force is constant. But here, with the same force, deformations are continuous, whatever may be the time. At different times, say continuous deformation. This is the classical difference between a solid and a fluid. Now let us see the difference between a solid and a fluid in a tabulation form. The first one is with the application of shear force or tangential force. So in case of a solid, if shear stress is applied, the body will undergo deformation, and this deformation is not continuous as long as the applied shear stress is constant. Now coming to fluids. In case of fluids, even if the applied force is constant, the deformation is continuous. We have already defined a fluid is a substance which undergoes deformation, continuous deformation, even if a small amount of shear force is applied. So the deformation is continuous. Now you can see this particular aspect in the form of an animation shown here. Now let us see what happens if the applied shear force is removed on either solid or a fluid. See, in case of solids, if the applied shear force is removed, deformation may be recovered, the shape may be regained. Now, in case of fluids, if we remove the applied force, the deformations are not recovered and the deformations are in fact permanent. Now, let us see the relation between the stress applied and the strain resulting in the case of solids and fluids. So, in case of solids, stress is proportional to strain. Let us say shear stress is proportional to shear strain. Tau proportional to phi. It is nothing but Hooke's law related to shear stress. In case of fluids, same shear stress applied, but it is not tau proportional to shear strain. Means shear stress is not proportional to shear strain. Then what it is? In fact, it is the shear strain rate of shear strain, or in some examples have seen simply shear stress is proportional to strain rate. Of course, you'll also come to know in future the strain rate is equal to the velocity gradient. So, it is the Hooke's law in case of solids. In case of fluids, it is in fact Newton's law of viscosity. Now, let us see a fourth differentiation. Solids are in fact elastic in nature. I told you earlier, Hooke's law, shear stress proportional to shear strain within elastic limit. So, solids are basically elastic in nature. So, coming to fluids, in fact they are viscous in nature. So, viscous in nature means, when a force is applied, a shear force is applied, so one layer will try to offer resistance against the motion of another layer, of course, which we see in the next unit. So, in a nutshell, solids are elastic in nature, whereas fluids are viscous in nature. Let us see the meaning of viscoelastic substances. It was one of the previous question in some competitive exam, I don't remember. We have already discussed solids will exhibit elastic nature or elastic behavior. Fluids will exhibit viscous nature. But there are certain substances which exhibit both elastic and viscous, both elastic and viscous nature. Such substances are called viscoelastic substances. Sir, can you give examples? Of course, the approximate examples are blood clot. Another example is Earth's mantle. You know the meaning of Earth's mantle, the inner part of the earth. These two, but there may be several other things. These are the examples for viscoelastic substances. In the earlier module, we have seen the difference between a solid and a liquid. Now let us see the main differences between liquids and gases. In order to explain them in a detailed manner, I'll use a PowerPoint presentation. Just go through it. Now let us see the difference between a liquid and a gas in a tabulation. The first differentiation is with respect to spacing of molecules. See, in case of liquids, the spaces are less compared to gases, means the molecules are more closer in case of liquids compared to gases. Suppose if you want to compare with respect to solids. So in case of solids, molecules are much closer compared to liquids, or in case of liquids, molecules are little bit far off compared to molecules in solids. Now coming to gases. So gases, spaces between molecules are large compared to liquids. Now let us see the force of attraction between different molecules. See, in case of liquids, the forces of attraction between different molecules are more compared to gases. This is the reason in case of liquids, generally free surface exists like this. Suppose you take the example of water. This is a free surface. Now, what is the meaning of free surface? One previous question actually in some exam. A free surface is the one subjected to atmospheric pressure only. Any other external pressures are in fact removed. Now let us see in the case of gases. See, in case of gases, the forces of attractions are very less. Since forces of attractions are very less, gases are more dynamic, and hence there will be greater freedom of movement by the gas molecules. Now let us see the comparison of volumes. In case of liquids, volume is definite. Why, sir? What is the reason? As we already discussed, the force of attraction in the case of molecules of liquids are high. Hence, the molecular spaces are closer, and hence liquids will have a definite volume. Now to gases. See, in case of gases, as we already discussed, the forces of attractions are very less, and hence the volume of a gas is in fact the volume of the container in which the gas is kept. The gas molecules expand to fill the entire space of the container. Now let us see the compressibility. Liquids have either low compressibility or practically I can say that incompressible. Now coming to gases, even a slight increase in pressure causes the considerable change in volume. I can say that gases are highly compressible. Now the liquid in a container without external pressure. Now here liquid is subjected to external pressure. You see the change in volume is negligible. It means practically the liquids are incompressible. Now gas without external pressure. Now see the container subjected to external pressure. The change in volume is considerable. Gases are highly compressible. I want to give a quantitative support for the incompressibility of liquids. I'll take the example of water. Assume a unit pressure, or let us say pressure of 1 atmosphere is applied on water. With this, the mass density is 998 kg per meter cube, mass density. Suppose you enhance the pressure to 100 atmosphere. Now the mass density increases to approximately 1001 kg per meter cube. Pressure has increased by 100 times, but whereas the increase in mass density is nominal. So I can say that liquids are almost incompressible, whereas gases are highly compressible. A fluid has continuum or continuum concept. In fact, if you see a real fluid, it may be a liquid or gas, there will be a number of molecules widely spaced. It means the spaces between different molecules are much higher. In case the spaces are more compared to the characteristic dimension of the body, say in case of a pipe flow, the diameter of the pipe, in case the spaces are considerable, then the classical principles of fluid mechanics cannot be applied and molecular approach must be used, and it becomes very complicated. So continuum concept is nothing but the idealization of the matter. Idealization of the matter in what form? As a homogeneous and continuous. If the fluid is assumed to be homogeneous and continuous, then the classical principles of fluid mechanics can be applied, and such a fluid is said to be continuum. It means this is assumption. I am assuming here the body with the molecules where the masses are continuously, closely, uniformly distributed. But practically it is not true. But to simplify the fluid flow analysis, this assumption is made. With the continuum concept validity, the mathematical tool of calculus can be used. Then you may have a question, sir, in case continuum concept is not valid, then what principles are to be used? As I already told, molecular approach, very complicated, or rarefied gas theory. Rarefied, R-A-R-I-F-I-E-D, rarefied gas theory. If continuum concept is not valid. Now let us see what is the mathematical relation. Any relation is there to verify whether a fluid is satisfying continuum concept or not. Medicine number, symbol K suffix N, it is equal to lambda by L. What is lambda? The mean free path. So what is this mean free path? We know, generally speaking, gases or fluids are highly dynamic. there will be number of collisions between different molecules. The space between two different molecules just before collision is called free path. Suppose we have number of collisions, let us say number of collisions. Say this is x1, x2, x3, x4, x5, x6, x7, x8, like this. The mean free path means the statistical average of the spaces between different molecules just before collision. I think it is clear. Now, what is characteristic length? Generally, it is a length measurement. Let us take the example of a pipe flow. The diameter of the pipe, say diameter of a pipe. Diameter of pipe is considered as the characteristic length. Now, when the continuous or continuum concept is valid, if the Knudsen number is less than 1%, means less than 0.01. So, if Knudsen number is less than 1%, we assume the fluid satisfying continuum concept. Now, let us see the examples where this continuum concept is satisfied. Let us see the examples where continuum concept is valid. Continuum concept means continuous mass distribution of molecules. In case of highly compressed gases, high dense gases, in case of high dense gases, continuum concept is valid. At the same time, liquids generally satisfy continuum concept. Examples where continuum concept is not valid. Continuum concept, mass distribution continuous, almost homogeneous. But where this is not valid? In case of low dense gases, I think you can easily understand. Low dense gases means gases are widely spread in a given volume. Molecules are widely spread. Mean free path is more. So, in case of low dense gases, this continuum concept is not valid. Also, generally vacuum flow is also where continuum concept is not valid. Now, I want to give which theories are to be adopted. As already discussed, the general classical fluid mechanics and principles what we are going to adopt in the coming topics assumes that fluid is continuum. Wherever fluid is not continuum, the molecular approach or rarefied gas theory is to be adopted. There is a classification of flows based on the value or range of Knudsen number. Of course, in this entire table, only this first one is important for gate and engineering services perspective. As already discussed, if Knudsen number less than 1% or 0.01, continuum concept is valid or fluid is assumed to be continuum. In case the range of Knudsen number is in between 0.01 and 0.1, it is called slip flow. Of course, slip flow is related to ideal fluids. We will discuss at the end of the first unit. Slip flow is related to ideal fluids. In case 0.1 less than Knudsen number, less than or equal to 10, it is called transition flow. Transition flow. In case Knudsen number more than 10, then it is called free molecular flow. Anyway, I repeat, only this first one is important. Continuing concept is valid as long as Knudsen number is less than 1%. Classification of fluid mechanics. First, fluid statics. The study of fluids in the state of rest or in equilibrium under the action of external forces. Under the action of external forces. Now coming to fluid kinematics, it deals with the fluids in motion, but without reference to the forces causing it, without reference to the pressure and its agent. So fluids in motion without reference to the forces or pressure on it. Now coming to fluid dynamics, similar to fluid kinematics, it also deals with the fluids in motion. However, it deals with forces causing it. So in case of kinematics, no reference to the external pressure or forces, whereas in the case of fluid dynamics, the external forces are considered in the analysis. Anyway, we will see these three different topics in different units. Now let us see the various systems of measurement that are generally used in fluid mechanics. The first is SI system, International Standard System. The second is MKS system. Of course, in the MKS system, absolute system is there, gravitational system is there. The third is FPS system, feet, pound, second, etc. So now among these three systems, the first one, SI system, is now generally used in India now, and in the competitive exams like engineering services or even GATE, most of the questions are in SI system. And of course, sometimes now and then in engineering services particularly, and in some of the state service commissions, they are asking with the MKS, of course MKS, gravitational system, they are asking. So now let us understand these two things briefly, SI and metric gravitational systems. In civil and mechanical engineering, four fundamental or primary dimensions are used. They are mass, length, time, and of course the fourth one is temperature. Of course, in electrical engineering you may have electrical current, etc. Let us not go into those details. So now let us see the mass. In case of SI system, mass, in fact, kg mass. Of course, sometimes this is also the unit of mass in metric absolute system. Okay, there is almost similarity. In case of metric gravitational system, metric gravitational system, is slug. Metric slug. Slug is the unit of mass in a metric gravitational system. So in some of the competitive exams, this question appeared, slug is the unit of mass. Okay. Now let us have a little bit additional analysis of this SI system. We all generally use the force. Force is equal to mass into acceleration. So what is the unit of force in SI system? Let us say Newton. So Newton is equal to mass. Of course, I am using kg mass. Acceleration, meter per second square. So now I want to give the definition of Newton using this SI system. Newton is the force required to induce a unit acceleration, say 1 meter per second square, of a unit mass, that is 1 kg mass. Suppose you go to metric gravitational system. So in case of gravitational system, metric gravitational system, force is represented by kg force. Kg force. In some of the previous IS prelims exams, pressure is expressed as kg force per centimeter square. But now we are habituated for SI system, means pressure is generally expressed nowadays in either Newton per meter square or Newton per mm square. So I want to convert this pressure in terms of kg force in terms of Newton. What to do? Very simple thing. 1 kg force approximately equal to 9.81 Newton. Yeah, 9.81 or 807. So approximately I am taking the value of Z as 9.81 Newton. So now I want to convert this. So 1 kg force per centimeter square is equal to 9.81 Newton. Okay, divided by centimeter square. So 1 centimeter is equal to 10 millimeter whole square. So you will get 9.81 by 100 Newton per mm square. If I want to convert into Newton per meter square, so this is equal to 9.81 by 100 Newton per mm square. If I want per meter square, so per meter, 1 meter is equal to 1000 millimeter. So you have to multiply with 1000 whole square. So how much you will get? 9.81 into 10 to the power of 4 Newton per meter square. And of course, most of you know 1 Newton per meter square as a Pascal. Anyway, those conversions we'll discuss in detail in the topic of pressure measurement. So, if you want to convert 1 kg force, 1 kg force is equal to 9.81 Newton. If you remember this, any other calculations you can project, work out easily. Now let us see the subscripts for various multiples and submultiples. Of course, most of you know these things. Kilo 10 cube, mega 10 to the power of 6, giga 10 to the power of 9, tera 10 to the power of 12. Now coming to the other side, milli 10 to the power of minus 3, micro 10 to the power of minus 6, nano 10 to the power of minus 9, pico 10 to the power of minus 12. Now there will be some general confusion with respect to symbols. So any unit in the name of a great scientist, we have to use a capital letter. We have to respect those great scientists by using capital letter. For example, you may say Newton. I'm intentionally writing small n. Actually, I should have written capital N. So Newton is represented by the symbol capital N. Suppose watt, the unit of power. What is a great scientist? Let us use capital W. So let it be any other thing in the honor of any scientist, any unit in the honor of scientist. Let us use capital letters. Properties of fluids. In this particular unit, we understand the basic definitions of mass density, weight density, specific gravity, specific volume, viscosity, compressibility and elasticity, surface tension, capillarity, vapor pressure, etc., etc. in detail. So coming to its importance, in the state service commissions in particular, this particular chapter has got very good weightage. And of course, in engineering services also, now and then regularly I say one question is appearing. But apart from the importance, if we can't understand this particular topic properly, it becomes very difficult to understand rest of the chapters in fluid mechanics and hydraulic machinery. Mass density. It is also called specific mass. What is the meaning of this? The mass of the material contained in a unit volume. Now let us see this particular slide. I am showing a unit volume. Let us consider the water is poured. Now density rho, unit is rho, is equal to mass per unit volume. So as I defined, the mass of the material contained in a given volume. Now let us see the units. The unit of mass is kg in SI system. I am following SI system. Volume means, say, meter cube. Therefore, mass density rho is equal to kg per meter cube. If I want to see the dimensional formula, mass m, ml power minus 3 in MLT system. Now let us see the mass density of various fluids. For water, 1000 kg per meter cube. For kerosene, approximately 8 to 10 kg per meter cube. And for mercury, 13,600 kg per meter cube. Now let us see the factors affecting mass density. First, effect of temperature. Generally, as temperature increases, the molecules move away from each other. As molecules move away from each other, the number of molecules in a given volume decrease. As the number of molecules decrease, the mass in a given volume will decrease. Therefore, as temperature increases, mass density decreases. Of course, there is an exception for water. What is that exception? Exception for water. Now, what is that exception for water? If temperature increases from 0 degrees to 4 degrees centigrade, instead of molecules moving away from each other, in fact, they become closer to each other in case of water. So therefore, what happens in this particular range of temperature, as temperature increases, mass density increases. After 4 degrees centigrade to higher value, what happens? As usual, as temperature increases, molecules move away from each other in a given volume, hence the mass density decreases. Now let us see the effect of pressure. As pressure increases, the molecules come closer to each other. So it means the number of molecules in a given volume increase. Therefore, as pressure increases, mass density increases. Now let us see the standard values of temperature and pressure. Temperature is 4 degrees centigrade for water, 20 degrees centigrade for gas, let us say air. Now coming to pressure, standard pressure, what we consider? It is 1 atmospheric pressure, which is approximately equal to 101.325 kilopascal. Effect of location. We know the acceleration due to gravity changes from location to location. But mass is constant everywhere. It means mass density is independent of acceleration due to gravity. Suppose the mass of a body on Earth is x kg. Then what is the mass of the same body on Moon? Same answer, x kg. So mass density is constant everywhere since it doesn't depend upon the acceleration due to gravity. Specific weight. The symbol is gamma or small letter w or rho g. Specific weight is also called as weight density. As usual, weight density is equal to the weight per unit volume. Weight is nothing but force. Weight is nothing but force. So therefore, mass into g, force, mass into acceleration due to gravity. By volume, I'll use the symbol capital V. We already discussed in the earlier topic mass density m by O. Therefore, weight density is equal to rho g. Now let us see the units of this weight density gamma. So gamma is equal to weight per unit volume. Weight is nothing but force. So force by volume. Force is equal to mass into acceleration. Volume L cube. This is nothing but m acceleration Lt power minus 2 by L cube. So this is equal to ml power minus 2 T power minus 2. Of course, you can use capital M instead of small m. Capital M, L power minus 2, T power minus 2. Sometimes if FLT system is used, you can simply say FL power minus 3. The unit of force in SI system is Newton. Therefore, force per volume Newton per meter cube. I am using SI system. Now let us see the effect of acceleration due to gravity on specific weight or weight density. We know gamma is equal to rho g. Now let us see this particular animation. So as seen in this animation, g value is changing from place to place. For example, you see at equator, it is approximately 9.78 meter per second square. If you see at poles, it is approximately 9.832 meter per second square. It means g changes from place to place. Hence, the value of specific weight or weight density also changes from place to place. Now let us see the weight of a body at the equator and at the poles of an earth. As seen here, the weight of a body at equator is mass into acceleration due to gravity at equator, which is nothing but mass into 9.78 meter per second square. Suppose at poles G value is more, 9.83 meter per second square. Therefore, the weight of the body at poles is mass into 9.83 meter per second square. Now let us see the weight of a body on moon. We know Z of moon is equal to approximately equal to 1/6 of Z of earth. Therefore, the gamma of a body on moon is equal to 1/6 of gamma of earth, which is the reason W means weight of a body on moon is equal to 1/6 of W of earth. You can see this using this animation. Now let us look into specific gravity. You see this image. Specific gravity is the ratio of densities. Densities of what? The mass density of a given fluid or a test fluid and the mass density of the standard fluid. Generally, in the case of liquids, water is considered as the standard fluid. Of course, I can take the ratio of weight densities also. What are the symbols? Specific gravity is represented by the symbol S or G. Sometimes we may also call it as relative density. So, as explained in the animation, specific gravity is equal to rho of a given fluid by rho of standard fluid, or gamma of the given fluid or test fluid by gamma of standard fluid. Now, what is the practical use of specific gravity? If I know the specific gravity of a substance, I can calculate the mass density or the weight density of that particular substance very easily from these relations. Suppose the specific gravity of a substance, let us say instead of fluid, a substance or a given fluid is 0.8. I want to know the rho of that particular fluid. Then what it is? Specific gravity given 0.8, rho of the fluid which we have to work out by rho of the standard fluid. I already mentioned the standard fluid is water, for which the mass density is 1000 kg per meter cube. Therefore, rho of the given fluid is equal to 800 kg per meter cube. Now, let us see the examples for specific gravity of various substances in this 2D animation. You see here animations. For water it is 1, kerosene 0.81 and mercury 13.6. Unit of specific gravity. As we have already seen, Specific gravity is the ratio of densities of test fluid and a standard fluid. Means ratio of similar properties. I think you can guess the unit of specific gravity. It has no unit because it is the ratio of similar properties. No unit, since it is the ratio of similar properties. Specific volume. The notation what I use is small v. Specific volume, it is the reciprocal of mass density. So mass density is rho. Therefore, specific volume is equal to 1 by rho. Rho means mass density. So if you see the unit, rho is equal to kg per meter cube in SI system. So the unit is meter cube per kg. Then what is its importance? In fact, specific volume is important in the case of gases. You will come to know in future, there is one equation called perfect gas equation. Perfect gas equation. So in this perfect gas equation, I will write here PV, capital V, is equal to mRT. P is equal to m by V RT. P is equal to rho RT, or P by rho is equal to RT. So here this particular 1 by rho is the specific volume. Of course, P means absolute pressure, R is the gas constant, T is absolute temperature. Of course, we discuss later this again. Now let us see pressure, the definition of pressure in case of hydraulics and the classification of pressures, and let us see whether pressure is a scalar or a vector. As we all know, pressure is the compressive force per unit area. Of course, you can say that pressure is the normal force per unit area. In case of hydraulics, it is the compressive force per unit area. Now let us see this animation. Now you see this particular point. So there is a point inside this water body. Pressure is same in all directions. Magnitude of pressure is same. But what about the direction? No specific direction. Since the pressure is same magnitude wise in all directions at a point, and since it has no specific direction, it is a scalar. Pressure is a scalar. Majority think that it is a vector, but it is not a vector. Pressure is not a vector. It is a scalar. Now, what is the unit of pressure? As I already told you, pressure is the force per unit area. Of course, it is the compressive force. Now, let us see the classification of pressures. I have shown a graph. So, here you have the absolute zero or complete vacuum. Now, on the y-axis, I am showing the pressure. Now, I have shown another line, local atmospheric pressure. So, what is this local atmospheric pressure? The pressure at a given location. Sir, whether local atmospheric pressure is constant? No. It may be changing from, or it will change from place to place. Since it changes from place to place, it is also called local atmospheric pressure. So, I want to know, there is another term called gauge pressure. So, what is this gauge pressure? Suppose there is a machine or there is another location where a machine is installed. In that, you have some magnitude of pressure. In the diagram shown, the pressure shown is above the local atmospheric pressure. Pressures measured above the local atmospheric pressures are called positive gauge pressures. Above the local atmospheric pressure. Now, suppose the pressure at a point or pressure in a machine is less than the local atmospheric pressure here, you see. Since the pressure is less than, it is called negative gauge pressure. Some professors call it as suction pressure or also vacuum pressure. So, pressures measured with respect to this local atmospheric pressure are called gauge pressures. So, gauge pressure may be positive or negative. Now, sometimes I may say simply the pressure is zero. What is the meaning of this pressure is zero? Practically, pressure is zero means it is the gauge pressure. It indicates local atmospheric pressure. Sir, I want to measure the pressures with respect to absolute zero or complete vacuum. Let us take P absolute is equal to P local atmospheric pressure plus or minus gauge pressure. Sir, when do you go for plus? You go for plus in case of positive pressure. You go for minus in case of negative or suction pressure. So, now you see, so with respect to absolute zero, the pressure at a point, this is absolute pressure. Now, again, this is absolute pressure. So, the absolute pressure is always positive, whereas the gauge pressure may be positive or negative. Just I will write this. Absolute pressures is always positive. Gauge pressures may be positive or negative. Now just for fun, I want to take one small simple numerical problem. You see here. Suppose local atmospheric pressure, let us say 101.5 kilopascal. Let us take. Assume the gauge pressure is equal to 1.5 kilopascal vacuum. I want to know what is the absolute pressure. We have the relation here. P absolute pressure is equal to local atmospheric pressure plus or minus gauge pressure. Now in this question, the gauge pressure is given as vacuum pressure. Vacuum pressure means negative pressure. I already told you, in case of negative pressure, use minus sign. Therefore, absolute pressure is equal to 101.5 kilopascal and the gauge pressure is negative pressure minus 101.5. Therefore, this is equal to 100 kilopascal. This is the absolute pressure. Suppose you have a positive value, you have to use plus sign. I think very clear to you. Now I want to ask you a question. The pressure in an automobile tire pressure, let us say in the automobile tire, the pressure is equal to 2.25 kg. Of course, you will find it as kg force per centimeter square. What is it? Is it absolute pressure or gauge pressure? So the automobile tire pressures mentioned are in fact the gauge pressures, means above local atmospheric pressures. Now let us see the bulk modulus and compressibility. Before understanding these concepts, let us come from fundamentals. Volume. Generally, volume is a function of applied pressure P and temperature T. Applied pressure P and temperature T. Of course, in this pressure, the effect of pressure, assuming temperature as constant, we come across the terms K. What is K? Bulk modulus. We come across beta, compressibility. Okay, so these are the terms with respect to pressure, assuming temperature as constant. Of course, if pressure is constant and for temperature, we get a term coefficient of expansions. Of course, I am not going to discuss much about this because this is somewhat thermal concepts of mechanical engineering. I will focus on bulk modulus and compressibility. Fine. So we have studied in strength of materials Young's modulus E. Young's modulus E or modulus of elasticity is equal to normal stress by normal strain, sigma by epsilon, normal stress by normal strain, Young's modulus. And we also studied G. What is G? Rigidity modulus. This is equal to shear stress by shear strain, shear stress by shear strain. Generally, gamma is used for the shear strain notation. Now, similarly, so Young's modulus, rigidity modulus, we have bulk modulus. In fact, bulk modulus is related to volume, volume changes, volumetric strain. So, what is this bulk modulus? So, bulk modulus is in fact change in pressure, change in pressure by volumetric strain. Okay, now we elaborate this bulk modulus. Now let us see the numerical equation for bulk modulus. So bulk modulus K is equal to change in pressure dP by volumetric strain. So any strain means change in a parameter with respect to original parameter. Here change in volume by original volume. Of course, some books they represent volume with this symbol, because if you simply write V, it represents sometimes velocity. So change in pressure by volumetric strain. But we know if pressure increases, volume decreases. So if numerator is increasing, denominator decreasing. So they are behaving in opposite directions. Since they are behaving in opposite directions, and all these moduli, Young's modulus, rigidity modulus, and bulk modulus are generally they are taken as positive values. Since I want to get a positive value, here what is happening? Numerator is increasing, denominator decreasing, or numerator decreasing, denominator is increasing. In order to get a positive value, I use minus. So bulk modulus K is equal to minus dP by dV by V. Of course, this is at constant temperature. Okay, fine. Sometimes I want to express this relation with respect to change in densities. How? What is the relation with respect to change in density? We know density is equal to mass by volume, or rho V cross multiplying is equal to mass. So this density change, volume change, but mass is constant. So this mass is constant. Now differentiate both sides. If you differentiate both sides, d rho to V plus rho into dV. Differentiation of constant is equal to 0. If you simplify, implies d rho by rho is equal to minus dV by V. I think you can understand now here. So bulk modulus. Now dV by V minus of dV by V plus d rho by rho. So here this minus gets cancelled. So this is equal to dP by d rho by rho. So generally in the exams, either on this or in this, numerical questions are appearing in several competitive exams. Of course, don't forget these are at a constant temperature. Okay, this is sufficient with respect to fluid mechanics, okay, of the bulk modulus. Now compressibility. So compressibility, I am using the symbol beta. So beta, compressibility is in fact the inverse of bulk modulus. Why, sir? Please explain. We know bulk modulus is equal to change in pressure by volumetric strain. Assume on the right side denominator is constant, means volumetric strain is constant, say some 1% of the volumetric strain. So assuming the denominator constant, if the value of K is more, the value of bulk modulus is more. If the value of bulk modulus is more means you need to apply more pressure. Change in pressure will be more. More bulk modulus, more change in pressure. More change in pressure required to have a particular change in volume. Means difficult to compress. Difficult to compress means compressibility is less. Okay. So let us see. K is more, or K is more difficult to compress because high pressure is required, means difficult to compress. K is less, easy to compress. So easy to compress means compressibility more, or else I will rewrite bulk modulus more, compressibility less, bulk modulus less, compressibility more. So therefore compressibility is nothing but inverse of bulk modulus. Now let us see the units. I will explain the units of both bulk modulus and compressibility simultaneously. Bulk modulus K, something like stress by strain. Strain has no unit. Therefore, the unit of bulk modulus is nothing but the unit of stress. So bulk modulus, unit of stress, unit of pressure. So this is nothing but Newton per meter square or Pascal. Now if you want to work out dimensional formula, I will not do it. You try dimension formula. You know the dimensional formula for Newton, you know the dimension formula for meter. Dear student, you please work out. Now similarly, if you want the unit of compressibility, inverse of bulk modulus na, so meter square per Newton. So your assignment is again work out the dimension formula for compressibility also. Liquids are generally taken as incompressible, whereas gases are highly compressible, you know. Why liquids are taken as incompressible in general? Let us take water. Let us take water. So in case of water, if you want to cause 1% change in volume, to have 1% change in volume, you know, the pressure, say atmospheric pressure, it must be increased to 210 atmospheres approximately. Okay, to have 1% change in volume, you have to increase the pressure, say one initial standard atmospheric pressure to 210 atmospheric pressure. This is in the case of water. Hence, liquids are generally incompressible. Now let us see the effect of pressure on bulk modulus. So this is the formula, bulk modulus dP by dV by V. So if pressure increases, say for a given volumetric strain, if pressure increases means K increases. Therefore, if pressure increases, bulk modulus increases. Now I want to compare the bulk modulus and compressibility of certain important substances like air, water, and steel. You know, compressibility is the inverse of bulk modulus. So compressibility, let us say beta of air by, I want to with respect to water, beta of water. So inversely, so this is equal to bulk modulus of water by bulk modulus of air. You see this, what is bulk modulus of water? 2.06 into 10 to the power of 9 by 1.03 into 10 to the power of 5. So this is equal to 20,000. What does it mean? It means air is approximately 20,000 times more compressible than water. 20,000 times more compressible than water, of course, at the conditions of approximately 20 degrees centigrade and 1 atmospheric pressure or 101.325 kilopascal. Now similarly, you can work out for water and steel also. Okay. Now let us say beta of water by beta of steel means ratio of compressibility of water and compressibility of steel. You work out here, you will get 100. What does it mean? It means water is approximately 100 times compressible compared to that of steel. So these ratios are being generally asked in public sector undertaking exams and state service commissions. Now let us see pressure wave velocity in fluids. Suppose water is flowing through a pipe. Say there is a valve. If the valves are closed, maybe gradually or suddenly, because of this closure of valves, the kinetic energy is destroyed. So kinetic energy is converted as pressure energy. So a pressure wave will travel through the fluid medium in the pipe. Of course, you will study this in detail in the chapter of flow through pipes. Now I want to say a small pressure disturbance will travel through the fluid medium with a velocity c. C is equal to pressure wave velocity. And of course, it is also nothing but velocity of sound or sonic velocity. So this pressure wave velocity is related to bulk modulus and mass density of the fluid. How, sir? C is equal to under root K by rho. This is also very important. C is equal to under root K by rho. Now I want to explain the pressure wave velocity C for isothermal conditions and adiabatic conditions. You might have studied isothermal means constant temperature. In case of constant temperature, bulk modulus is equal to pressure. You know, pressure is equal to rho RT for perfect gas. So therefore, pressure wave velocity C is equal to under root K by rho. K rho RT by rho. This is equal to under root R. Now coming to adiabatic process, same logic. C is equal to under root K by rho, but K is equal to small k into P. Here I want to give one clarity. Bigger capital K bulk modulus, small k is equal to Cp by Cv. It is nothing but Cp, specific heat at a constant pressure by specific heat at a constant volume. Right, C is equal to, I am repeating, this is small k, this is capital K. Mechanical students generally use the symbol gamma for this in place of small k. Okay, so small k into rho RT by rho. So rho cancel. So this is equal to under root small k into RT. Our mechanical students use gamma into RT. Sir, is it there in GATE syllabus? So generally in GATE, civil or mechanical, in fluid mechanics, they may not ask this type of approach. But I have seen most of the state service commission exams in India, they have this in syllabus. They are asking questions on this particular area. If you are for only for GATE exam, please don't see this particular concept. Mach number, capital M suffix A, Mach number. So what is this Mach number? Mach number is generally given by the formula V by C. Sir, what is this V? V is equal to velocity of fluid or body. Velocity of fluid or body. Sir, what is? Suppose air is blowing, air is moving against a chimney. It is the velocity of air. Suppose a rocket is launched in the air. It is the velocity of rocket. So the moving part. See, already discussed, sonic velocity or velocity of sound or pressure wave velocity. Okay, clear. Now based on the Mach number, the flows are classified in different style. Okay, if Mach number less than 0.3, if Mach number less than 0.3, fluids are generally treated as incompressible, means almost change in volume is 0 if the Mach number is less than 0.3. I have a submission. Some books have given this value as 0.2. Different books are giving different values. Okay. If Mach number less than 1, it is called subsonic flow. Subsonic flow. If Mach number approximately equal to 1, sir, what does it mean? 0.8 less than Mach number less than 1.2, then it is called transonic flow. Transonic flow. Again, I have another submission. Some books have given this as 0.9 less than MA less than 1.2. If Mach number is equal to 1, then it is called sonic flow. I will continue. If 1 less than Mach number less than 3 means Mach number is in between 1 and 3, it is called supersonic flow. If Mach number more than 3, then it is called hypersonic flow. Again, I have a submission. This particular analysis, these numerical values, in fact, not important for GATE exam, but they are important for various PSUs and state service commissions. Compressibility of water. Water is a liquid. I already discussed earlier that the compressibility of liquids is very less, or practically liquids are incompressible. Even then, the compressibility of water is considered in one of the analysis of fluid mechanics. I think you can guess. You might have studied a concept called water hammer or hammer blow or knocking, or you'll come to know in future. Don't worry, in the chapter flow through pipes. I already mentioned earlier, when the water is flowing through a pipe, if valve is suddenly closed, the kinetic energy is destroyed, pressure energy increases. So a high pressure wave will travel in the reverse direction, resulting in a maximum rise in pressure. In such cases, in sudden closure of valves, the compressibility of water is considered. So compressibility of water considered in sudden closure of valves in pipelines. Now let us take one simple question on bulk modulus and coefficient of compressibility. Take this question. You read the question. A reservoir of capacity 0.01 meter cube. Okay. It's given volume is equal to 0.01 meter cube. Volume, I use this symbol. Is completely filled with a fluid of coefficient of compressibility of 0.75 into 10 to the power of minus 9 meter square per Newton. It's not Newton per meter square. It means beta, coefficient of compressibility. This is equal to 0.75 into 10 to the power of minus 9 meter square per Newton. Now what happened? The amount of fluid that spills over in meter cube, if pressure in the reservoir is reduced, pressure is reduced, delta P, change in pressure, 2 into 10 power of 7 Newton per meter square reduced. So if pressure is reduced, what happens? More pressure, less volume. Less pressure, more volume. So what is the spillover? Okay, very simple. We know coefficient of compressibility is equal to inverse of bulk modulus. This is equal to minus dV by V by dP. Here pressure is decreasing. Since pressure is decreasing, you see, pressure is decreasing, So this minus will become plus. Okay. Anyway, I'll work out now here. Now beta is equal to dV, change in volume. I want to work out change in volume, divided by, what is the initial volume? 0.01 divided by change in pressure or dP. Okay. 2 into 10 to the power of 7 Newton per. Okay. 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 Right. Now if you simplify, you will get 1.5 into 10 to the power of minus 4 meter cube. This is the spillover. Therefore, option B is the correct answer. Now another question, a numerical answer question, fill up the blank type question. Determine the velocity of sound in air if the mass density of air at atmospheric pressure of 1 bar is 0.92 kg per meter cube. Okay, so I will work out here. Pressure is equal to 1 bar. So 1 bar means 100 kilopascal. So this is equal to 10 to the power of 5 Pascal. I think no doubt. Now mass density. So mass density rho is equal to 0.92 kg per meter cube. Now what is the velocity of sound in air? So we know C is equal to under root K by rho. Sir, K is not given, but earlier we discussed K, bulk modulus, is equal to the pressure in case of isothermal systems, isothermal process. So let us assume here, if nothing is mentioned, isothermal process. So this is equal to under root P by rho. So this is equal to under root P is equal to 10 to the power of Pascal. Pascal means Newton per meter square divided by 0.92. If you use virtual calculator, you will get approximately 330 meter per second. Suppose in this problem, suppose a rocket or a jet fighter is traveling or moving with a velocity of 1800 kmph, speed of jet fighter. So what is the Mach number? So 1800 kmph, na, you please convert into meter per second. So 1800 into 5 by 18, you will get 500 meter per second. Now I want Mach number. So Mach number is equal to V by C, already over. So this is equal to 500 by 330. So 500 by 330, you will get somewhere between 1.5 and 2, that you can work out, right? So it is more than 1, less than 2. Now suppose the paper setter may ask another question. What type of flow it is? What type of flow it is? Type of flow. This extension. Here 1 less than Mach number, because Mach number is here more than 1 and less than 3. So 1 less than MA less than 3. What type of flow it is? Supersonic flow. Let us see this question with respect to bulk modulus and compressibilities, etc. The pressure on a given mass of a liquid is increased from 3 megapascal to 3.5 megapascal. change in pressure. 3.5 to 3 minus 3, 0.5 megapascal. 1 megapascal is equal to Newton per mm square. So 0.5 into 10 to the power of 6 Newton per meter square. This is change in pressure. The density of the liquid increases from 500 to 501. D rho, change in density, 501 minus 500, original density. So 1 kg per meter cube. Now what is the average bulk modulus? So I will come here. Average bulk modulus K is equal to dP by d rho by rho. dP 0.5 into 10 to the power of 6 by 1 kg per meter cube, dP by d rho by rho. 1 by 500. So if you simplify this you will get 250 into 10 to the power of 6 Newton per meter square. It is nothing but 250 megapascal. Therefore, answer D is the correct answer. Hi friends, let us now discuss the property viscosity of fluids. We see in our daily life when two solid bodies move against each other, or if you want to move them against one another, we have to apply some horizontal force, then only they can move relative to each other. You take an example, you take a table, say of 4 legs, try to pull it on a floor without applying a horizontal force of certain magnitude. I am using the word certain magnitude. Whether the table will move? No. If the applied force is beyond a certain range, then only the table will move. When it will move? When the friction between the legs of the table and the floor is less than the applied horizontal force, or the applied horizontal force is more than the frictional force between the legs and the floor, then only it will move. So you might have studied in engineering mechanics a term, coefficient of friction. Similar to this friction between two bodies, there is a term called viscosity of fluids. Suppose you try to move in air, you try to move in water. Where do you find more comfort in moving? We find more comfort in moving in air rather than water. Same case, try to move in an oil tanker. Let us take example. You will find more resistance against motion in oil tanker. It means there is some internal resistance in case of fluids. The fluid may be a gas or a liquid. So this internal resistance of fluids is in fact called viscosity. Now let us take a small video. You try to drop honey in the vertical direction as shown here. It will have a free falling velocity. Suppose you now drop water as shown here. You observe which fluid will have more velocity. Naturally, the water will have more velocity while falling. Suppose you take some other oil, you observe the velocity of flow. So what is the reason here? Honey being thicker has more internal resistance, means more viscosity compared to air. Or you might have seen, you might have studied in your 7th class or 8th class. You see here, take a steel ball, small steel ball, drop it in a cup of honey. Same steel ball, try to place in a cup of water. Very simple, easily you can understand. The ball moves with less velocity in case of honey. Same reason, internal resistance, that is viscosity of honey, is more than that of water. So similar to solid bodies, we do have some internal resistance named as viscosity in case of fluids. So it is a very beautiful, fantastic concept which we discuss in detail in several ways. Now let us see the complete definition of viscosity of fluids. You see the diagram here. I have shown a laminar flow between two plates. So the bottom plate is a fixed one. The top one is a moving plate due to an external force F. Now you are able to see differential velocity of different layers. So what is the reason? Now you see another diagram. So in this you can see the bottommost layer has got zero velocity, same as that of the static plate shown. The top layer of fluid has the same velocity as that of the moving plate. So relative velocity 0 means no slip condition. So wherever the relative velocity of two adjoining bodies or adjoining fluid layers, whatever it may be, is 0, it is called no slip condition. Anyway, let us come to the definition of viscosity again. So viscosity is the internal resistance against the motion of two adjoining layers. Internal resistance against the motion of two adjoining layers. Now let us see the units of viscosity. First let us take up SI system. You know, mu is equal to tau by du by dy, because tau is equal to mu dot du by dy. So what is the unit of shear stress? So shear stress is something like stress Pascal. So what is the unit of du by dy? Velocity gradient. Du by dy. Earlier we have seen this is also equal to d phi by dt. I can explain the unit of either du by dy or d phi by dt. Suppose if you take d phi by dt, what is the unit for angle? No unit. No unit. D phi, no unit. But what is the unit of dt? Second. 1 by second or s power minus 1. Sir, you please explain with respect to du by dy. Suppose du by dy. Velocity, numerator is velocity, meter per second. Y is nothing but meter. So very simple to understand, 1 by second or per second. So therefore, the unit of viscosity is tau is Pascal du by dy 1 by second. So this is nothing but Pascal second. Sir, you explain with respect to Newton's, sir. We all know what is Pascal, Newton per meter square. Newton per meter square into second. Newton second per meter square. We know Newton is the force required to impart unit acceleration of 1 meter per second square on a kg mass. So 1 Newton is equal to 1 kg, 1 acceleration, unit acceleration, 1 meter per second square. Okay, so this is Newton. Now therefore, viscosity mu is equal to Newton kg meter per second square into second by meter square. If you simplify, meter cancel, 1 second cancel. Therefore, mu is equal to kg per meter second. Now let us see the dimensional formula for viscosity. Just now we derived viscosity has the unit of kg per meter. So what is kg? Is nothing but mass. Meter, 1 by meter, L power minus 1, 1 by s, T power minus 1. Therefore, the dimension formula for viscosity is m into L power minus 1, T power minus 1 R. Easy to remember, m by Lt. Now let us see the CGS units of viscosity. CGS system. In CGS system, viscosity unit is poise. So what is this poise? Named in the honor of the great Poiseuille. So what is this poise? Let us see here. mu is equal to, already we have seen, Newton second per meter square. This we have also seen as kg per meter second, kg 10 cube, gram, meter 10 square, centimeter into second. If you simplify here, you will get mu, poise. Actually, what is this poise? I forgot earlier. This is nothing but 1 gram per centimeter second. Now you see here, this is nothing but 10 grams per centimeter second. This is nothing but poise, implies 1 Pascal second is equal to 10 poise. It is poise, not paisa. Or in majority of the numerical questions, they are giving the viscosity in terms of poise. Then what to do? 1 poise is equal to 0.1 Pascal second. So you must be in a position to convert from one system to another system. Now I want to analyze the effect of temperature, a numerical approach on dynamic viscosity initially, then followed by kinematic viscosity. Of course, the conceptual part I have already done. Say x-axis is temperature, y-axis dynamic viscosity. We have already seen. In case of liquids, as the temperature increases, dynamic viscosity decreases. This is in the case of liquids. I am giving a numerical or graphical analysis. So in the case of gases, already you know, as the temperature increases, molecular action increases, collisions increase, resistance increases. So in case of gases, as the temperature increases, viscosity increases. First, I want to explain the effect of temperature on dynamic viscosity of gases. The kinetic theory of gases predicts that dynamic viscosity of gases is directly proportional to square root of temperature based on experiments. An experimental formula or empirical formula, better wording, nu of gases is approximately equal to AT power half divided by 1 plus B by T. What is T? T is absolute temperature. I need not tell you about absolute temperature. A and B are two constants. Sir, how do you work out these constants? Suppose if you can measure viscosity of gases at two different temperatures, Nana, two different temperatures. Why, sir? 2, why not 3? So in this expression, how many unknowns are there? A and B are unknowns, two unknowns. For two unknowns, I need two different equations to work out the unknown constants. You conduct or you measure viscosity of gases at two different temperatures. Measured at two different temperatures, unknowns A and B. Two experiments are sufficient to work out two unknowns. So A and B are two constants which can be worked out experimentally by taking
viscosity of gases at two different temperatures. So for viscosity of gases, it is directly proportional to square root of T based on prediction of kinetic theory of gases. Now let us see the effect of temperature on dynamic viscosity of liquids numerically. Of course, dynamic viscosity of liquids decrease with the temperature. So there is an approximate relation. Empirical relation means based on experiments. This is dynamic viscosity of liquids is equal to A into 10 power B by T minus C. Sir, what is T, capital T? Guess absolute temperature. Then A, B, C are constant, three constants. I think you can understand how to work out the constant by experimentally finding out the measuring the viscosity of a liquid at three different temperatures, three unknowns, three experiments, three equations. You can work out variation. This is again, I am repeating, an empirical relation. Anyway, don't break too much. So if you are unable to remember these formulae, just forget. But in case of some exams, some competitive exams, they are asking the relations. Okay, right. Now let us see another simple conceptual question. Dynamic viscosity is a fluid property realized in motion of fluid. Dynamics, motion. Yes, in fact, viscosity is the property of a fluid realized when it is in motion. Of course, the very definition, viscosity is the resistance against motion of one layer of fluid over another layer. Anyway, A is correct. Now let us see other options. It is a property in the state of rest. Wrong. First one is right. It is a property with a unit of Pascal. No. See, unit of viscosity, you know, one is Newton second per meter square. You know, Newton per meter square is nothing but Pascal. So therefore, the unit is Pascal second. It's not Pascal. So this is wrong. Now in MKS system, it seems we have already derived. Na? Come on, what is the unit in MKS system? kg per meter second or m by LET. You see here, some confusion is there. Na? So this is also wrong. So dynamic viscosity is a fluid property realized in the motion of fluid. Rest of the three statements are wrong. Now let us see a theoretical question on factors affecting viscosity. Of course, now with respect to temperature, an assertion reasoning question or statements question which appeared in IES but a classical question. Let us see now. So statement 1. In general, viscosity in liquids increases and gases it decreases with rise in temperature. Just visualize yourself, right or wrong. Okay. Second statement, viscosity is caused by intermolecular forces of cohesion and due transfer of molecular momentum exchange between fluid layer, of which the liquids, the former, and in gases, the latter, contribute the major part towards viscosity. Now you have to understand which statement is true and whether statement 2 is the reason for statement 1 or not. So first statement, it is related to effect of temperature on viscosity. Okay. Let us go back. Y-axis is viscosity. X-axis is temperature. So we have already seen in liquids viscosity is primarily due to cohesion. As the temperature increases, cohesion decreases, and hence viscosity of liquids decrease with the increase of temperature. We have already seen. Now, in case of gases, it is a molecular momentum exchange. So, as the temperature increases, the dynamics of molecular momentum increases. More molecular momentum, more viscosity. So, as the temperature increases, viscosity of gases increase. This is in the case of liquids. This is in the case of gases. So, now you see what is the statement 1, true or false? Viscosity in liquids increase. Wrong. So, statement 1 is wrong. Statement 2, yes. In case of liquids, viscosity is due to cohesion, and gases, molecular momentum exchange. So, statement 1 is correct. Statement 1 true. Statement 2 false. So, that is answer. Statement 1 is true and statement 2 is wrong.
According to calculus, in case of small angles, we know that d phi is equal to tan of d phi. Now, let us see the proof that the rate of shear strain is equal to velocity gradient. So, as seen here, d phi, that is shear strain, is equal to AA dash minus CC dash, this opposite side, by adjoining side. What is that adjoining side? AC. Now, what is AA dash? So, AA dash is the distance traveled by the layer AB in an infinitely small interval of time dt. So, what is the velocity of the top layer? As seen here, u plus du. U plus du in a time interval of dt minus CC dash. What is CC dash? The distance traveled by that bottom layer. What is the velocity of that bottom layer? U. U in small interval of time dt. Fine. Divided by. So, what is AC? That AC is nothing but dy. Now, you simplify. On simplifying, you will get du dt by dy implies d phi by dt is equal to du by dy. So, hence we have proved that the rate of shear strain is nothing but velocity gradient. Implies, according to Newton's law of viscosity, tau is equal to mu dot du by dy. Now let us see velocity gradient as the slope of a tangent. Here the velocity profile between the two plates as discussed earlier. Now I want to draw a tangent here. You see here now. Tan theta. Now I want to show enlarged u. Du by dy with respect to y-axis. Now generally what we do in case of strength of materials, say x-axis, let us say strain, it is independent, y-axis stress dependent. Suppose you have a curve like this, you want a tangent here, we show the slope with respect to x-axis, which is independent parameter. But now in the case of this velocity gradient, I have shown this theta with respect to y-axis. Why, sir? See, definition is with respect to independent variable. So in the case of flow between parallel plates, what is the independent variable? The gap between the plates, y, is the independent variable. Sir, what about velocity u? See, velocity u is not independent. In fact, it is the dependent variable which varies with respect to the distance from the fixed plate. So I think you are satisfied with why I have shown theta with respect to y-axis here. Now I want to explain further. Take another tangent here. Now here if you see, the slope of this tangent is much higher compared to the slope here. It means in this flow phenomena, the slope is more near the bottommost plate, whereas the slope is less near the top plate. Okay, so I have explained the velocity gradient as the slope of the tangent. Till now we have seen the velocity profile as a nonlinear profile. But in solving majority of the problems related to viscosity, we consider the velocity profile as a linear profile. How it is valid? Suppose du by dy. When the thickness is very small, so mathematically we can go for du, the difference in velocity. Let us say this as delta u divided by delta y. Fine. Now, under what conditions? Okay. Now let us see what is the delta u. It is nothing but topmost velocity u, bottommost velocity 0 divided by h. Du by dy is equal to u by h. So there are certain conditions in which we can assume linear velocity distribution. What are those conditions? Conditions for linear profile. This is one previous IAS objective question. So linearity can be assumed if point 1, the gap between the plates is very small. So what is the meaning of small? Sir, how much it is, sir? Is it 1 mm, 2 mm, etc.? Generally, in solving the problems, you have to read the data carefully. If paper setter is silent about the velocity distribution, mathematical relation for a velocity distribution, assume it as linear distribution. In most of the cases, we take it as linear distribution. The second condition is dp by dx is equal to 0. What does it mean? The pressure gradient is 0 in the direction of flow. Now it appears to be a Greek and Latin. We will discuss this in detail in the case of laminar flow. So the velocity profile is generally assumed as linear in solving many of the problems if data is not given with respect to velocity distribution. The assumptions involved are the gap between the plates is small, and another condition will be the pressure gradient with respect to the direction of flow dp by dx is equal to 0. I think you have understood.
Now let us take the fundamental question. Newton's law of viscosity relates shear stress and shear strain. In order to understand this question, we know tau equal to mu dot du by dy. Okay. We also know du by dy is equal to d phi by dt. Okay. So it deals with shear stress. Yes, shear stress. Mu viscosity. Du by dy is in fact velocity gradient. Velocity gradient. So in these four options, nowhere velocity gradient is mentioned. d phi by dt, actually phi represents shear strain, but it is not shear strain. It is shear strain rate. Some professors simply say strain rate. Shear strain rate. So Newton's law of viscosity deals with shear stress, shear strain rate, and viscosity or dynamic viscosity. So naturally option D is correct. In the derivation of Newton's law of viscosity, certain assumptions are made. Now I want to create a question on this. You see here, select the correct assumptions in Newton's law of viscosity. There are three assumptions made. Let us read slowly. Fluid particles move in a particular direction maintaining straight parallel lines. Straight parallel lines. Of course, in future you'll come to know straight parallel streamlines. Okay, that is the first assumption. Let us see. Second, when a flow is adjacent to a surface, stick to it and have zero velocity relative to the boundary, which is called no slip condition. Think. Okay. Other fluid particles attempting to slide over them are retarded because of an interaction between faster and slower moving fluid, a phenomena that gives rise to shearing force. Of course, some professors call this a shear flow. Okay, second assumption given here. Third, shear stress on an interface tangent to the direction of proportional to the distance rate of change of velocity. Distance is here. Distance. That's very important. Now let us see what are the correct things. To analyze this, I'll take a diagram here. You see here, there are two plates. Plate, bottom plate, you see here, hatched one. Hatched one means one is moving plate. Okay, moving plate. So in between stationary and the moving plates, I have shown some. See, near the stationary plate, u is equal to 0, na? U is equal to 0 means no flow. It is nothing but no slip condition. First, you see flow lines are parallel, na? Therefore, assumption 1, correct. Second, assumption 2, yes, no slip condition, correct. Let us further read. Other fluid particles attempting to slide over them are retarded because of an interaction between faster and slower moving fluid, a phenomenon that gives rise to shear force. Yes, see, without shear force, shear stress will not be there. So what happens? Near the solid plate, stationary plate, velocity 0. As you move away, the fluids will try to flow with a higher velocity. Below, layers with less velocity. So these less velocity layers will try to retard the faster moving layers. Yes, that is also correct state assumption. So second assumption is also involved in Newton's law. Third, shear stress on an interface tangent to the direction of flow is proportional to the distance rate of change of velocity. Yes. So what is that x-axis? X-axis is u. What is y-axis? So this y-axis is yes, y-axis is nothing but distance from the stationary plate. So we have already seen in Newton's law, the fundamental assumption is, the fundamental relation is tau proportional to d phi by dt, means shear strain rate. Shear strain rate is nothing but velocity gradient du by dy, du by dy. It means, what is that third assumption? Proportional to distance rate of change of velocity. Distance rate of change of velocity means du by dy. So tau proportional to d phi by dt or proportional to du by dy, or some professors say rate of angular deformations. So from this, all the three statements are correct. Therefore, option D is the correct answer. Now let us see a numerical question related to Newton's law of viscosity. The gap between two parallel plates kept 3 mm apart is filled with an oil of viscosity 2 pi. I want to write the data now itself. Given data. Gap between the plates 3 mm. Okay, I say dy is equal to 3 mm. Filled with an oil of viscosity 2 pi. Viscosity 2 pi. You know, pi is nothing but dyne second per centimeter square. It is a unit in CGS system. I already derived earlier. 1 Pascal second is equal to 10 pi, or 1 pi is equal to 0.1 Pascal second. Therefore, 2 pi is equal to 0.2 Pascal second or 0.2 Newton second per meter square. Okay, fine. The shear stress on the fixed plate, where is the fixed plate? The bottom plate. So the fixed plate, bottom plate, where the velocity is 0, no slip condition. The upper plate is moved with a velocity of 1.5 meter per second. I say du. Top velocity minus bottom velocity. See, bottom velocity I assumed no slip condition. So this du is nothing but 1.5 meter per second. I want shear stress. Tau is equal to mu dot du by dy. Of course, here there is one assumption. Sir, how do you know that the velocity distribution is linear? Of course, in this, the paper setter has given the diagram. In case the paper set is not given, suppose it is some IES conventional question or SSC JE conventional question, you have to write an assumption. Assume the gap between the plates is small. Whenever the gap between the plates is small or thickness of the fluid layer is small, linearization of velocity distribution can be assumed and Newton's law can be applied straight away. So here I am assuming linearization, assuming the fluid thickness is very small. So now tau mu dot du by dy, very simple, equal to mu 0.2 Newton second per meter square into du 1.5 meter per second divided by dy 3 mm means convert into meters 0.003 meters. If you simplify, you will get tau is equal to 100 Newton per meter square. Is the answer. Now let us see another question, a common data question. Of course, it was in the previous gate pattern or same can be asked in IES mains conventional question. See the question. I'll read out. A circular shaft of 100 mm dia rotates about its axis inside a fixed cylinder of a tube 106 mm. Inside is rotating 100 mm. Okay, I say, I will write the data. Di, what is the diameter of the shaft? Dia of rotating shaft is equal to 100 mm. Okay. Now, it is rotating inside a fixed cylinder of tube of 106 mm internal diameter. See, shaft is rotating inside a fixed one. Okay, good. Now, and length of 150 mm. Anyway, I say the fixed tube dia as out is equal to 1 dia of fixed tube 106 mm. Okay, right. So length of the shaft 150 mm. Okay. The space between the tube and the shaft is filled by a lubricant oil of dynamic viscosity 2 pi's. We have already seen earlier question 0.2 Newton second per meter square. The shaft is to rotate at a speed of 240 rpm revolution per minute. Okay, so n is equal to 240 rpm. Okay, right. Now assume linear variation of velocity profile across the gap and fluid behaves as a Newtonian fluid. Now what is the first question? Now see, this entire data is shown in the diagram. Okay, I think you can see very easily. Okay, now what is the first question? The shear stress on the shaft, rotating shaft is, okay. I'll draw a rough sketch. Please cooperate, I am very poor in drawing. This is the inner shaft rotating. This is the fixed shaft, sorry, fixed tube. So now outer side 106 mm, outside side 106 mm, and inside dia is 100 mm. Therefore, what is the thickness of the film? Thickness of oil film. So 106 minus 100 whole divided by 2. This is equal to 3 mm. Okay. Right. Now I want to know the shear stress on the shaft. Let us work out here. Tau is equal to mu dot du by dy. Mu viscosity known. Du. How do you work out this u? So here near the fixed shaft, sorry, fixed tube, velocity 0. We already assumed no slip condition. Shaft is rotating, okay. So it will have a tangential velocity, okay. So I'll work out here. What is u? This is u. Pi dn by 60. What is that d? Inner dia of shaft. Because shaft is rotating. So P di n by 60. So outside is 0. So in this you have the shear stress like this. You have to work out. Okay. So shaft is rotating like this. Okay. So now dy means the film thickness. So simple, mu is equal to 0.2 into du pi internal 100 mm. I will convert into meters, 0.1 into n rpm 240 pi dn by 60. This is du. dy 1 by, what is the gap? 3 mm, 0.003. If you simplify, you will approximately get 83.8 Newton per meter square. Now the second part of the common data question. Power to overcome the viscous resistances. Okay, I will work out. Power is equal to torque into omega, angular velocity. It also can be written as force into velocity. Both the things are correct, but I find personally the second as easy. Sir, what is this force? This is nothing but shear force. So what is this? Shear stress into shearing area, okay, into velocity. What is velocity? Tangential velocity, of course. Pi di n by 60. See, tangent velocity means internal shaft rotation. Okay. So shear stress already worked out. 83.8. Shearing area. Area of the shaft, internal area of the shaft. What is that? Length into pi d. Shaft pi di into L, shearing area, into pi din by 60. So 83.8 into pi internal 0.1, 150 mm, 0.15 meter into pi into 0.1 into 240 by 60. Solve it. You'll get the answer as, I think, 4.95 watt. That's all. Now let us take another question. A 100 Newton block slides down a 30-degree inclined plane. The plane is lubricated by a 2 mm thick film of oil of specific gravity 0.8 and viscosity 10 poise. Contact area is 0.1 meter square. The terminal velocity of the block in meter per second is. Okay, right. I want to draw the sketch again. This is an inclined plane. Okay. This is theta, 30 degrees. So on this, a block its weight W. Okay. So there is a gap here, clear gap of how much? 2 mm. 2 mm gap. I say this as Y. Okay. Okay. Right. Now I want to know the terminal velocity. So in order to solve this problem, let us take equilibrium. So the body has self-weight W. I want to resolve this self-weight in the direction of the inclined body. So what is this? You know, this is 30 degrees. Say this is also 30 degrees. So naturally, this is equal to this 30. This is 90 minus 30. So this is W sine 30. I think simple mathematics, I need not tell W sine 30. Now, along this inclined plane, I will resolve the forces. Downward force is equal to upward force along the inclined plane. This is the downward force due to self-weight. Upward force is nothing but the shear force. Okay. So for equilibrium, downward force along the plane W sine 30 is equal to upward force shear stress into area of the block. So what is self-weight? It is given as 100 Newton. I think it's given as 100 Newton. Sine 30 is equal to half. Tau. Mu, viscosity, 10 poise. 10 poise is equal to 1 Pascal second or 1 Newton second per meter square. Tau. Mu. dV. Yes, I want to know the velocity. dV means V minus 0. Near the inclined body, no slip condition, zero velocity. So V minus dV by dy. Dy is nothing but 2 mm, 0.002. So area of the block, it's given area of the block as how much? 0.1 meter square. If you simplify, implies V is equal to, do it slowly without calculator also you can do, you'll get the answer 1 meter per second. Now let's see non-Newtonian fluids. The term itself indicates the fluids which do not satisfy Newton's law of viscosity are called non-Newtonian fluids. The study of non-Newtonian fluids is in fact called rheology, you may be knowing. Now let us have a detailed discussion of this. According to Newton's law of viscosity, suppose tau proportional to du by dy. Tau is the shear stress, du by dy is rate of shear strain, right? Tau proportional dv by dy. So now mu is equal to tau by du by dy. This is generally what we studied in Newtonian fluids. And in case of Newtonian fluids, in fact, this is constant. And this is linear relation. So this is with respect to what we studied for Newtonian fluids. Now in case of non-Newtonian fluids, yes, tau proportional to du by dy. But it's not linear, in fact non-linear. Now here the term related to viscosity is apparent viscosity. I use the suffix a, apparent viscosity. So what is this apparent viscosity? Tau by du by dy. It appears to be same as ordinary dynamic viscosity from Newtonian fluids and apparent viscosity of non-Newtonian fluids. It appears to be same, but in fact here the dynamic viscosity of Newtonian fluids is constant, but here it need not be constant. And of course, to explain this apparent viscosity and various parameters of non-Newtonian fluids, there is a law called power law. So we are going to discuss power law now. Power law. What is this power law? Tau is equal to tau y plus a into du by dy whole power n. Now let us understand each and every term here. Tau, as usual, the applied shear stress, as you know that. Tau y. Tau y is the minimum yield stress. Minimum yield stress to start deformation. Of course, some professors use the symbol tau naught also, but I am habituated to use the word letter tau y. Minimum yield stress to start deformation. A, it is a multiplying index, multiplying factor or index. We will see what it is. So n is the power index. So depending upon the values of A and N, there are varieties of non-Newtonian fluids. Of course, these values depend upon the conditions imposed and the situations, temperature, time, etc., various parameters. So depending upon various conditions of A and N and the value of tau, non-Newtonian fluids are further classified into several types. So these non-Newtonian is a broad category. One is time independent. Here, time dependent. And of course, you already know Newtonian fluids are time independent. In case of non-Newtonian fluids, again there are two subtypes, time independent and time dependent. So what are various fluids that come under time independent? One is pseudoplastic. The second is dilatant. And of course, there is another word, another one, Bingham plastic. So these three are time independent non-Newtonian fluids. Now coming to time dependent, you have thixotropic and of course rheopectic fluids. Okay, so this is the broader classification of non-Newtonian fluids. Now this is power law. I want to explain dilatant fluids. So in this power law, for dilatant fluids, tau y is equal to 0. Tau y is equal to 0 and this power index n more than 1. Now tau is equal to A into du by dy whole power n. I rewrite mu apparent du by dy. So then what is mu apparent in terms of A? So tau is equal to A into du by dy whole power n minus 1 into du by dy. Now you compare this equation and this equation. So mu apparent or mu small a is equal to a into du by dy whole power n minus 1. This is dilatant fluid. Now some professors call dilatant fluid as shear thickening fluids. So dilatant fluids are also called shear thickening fluids. Sir, why it is called shear thickening fluids? So to understand this, because it's one previous engineering services question, why it is called shear thickening fluids? So let us understand graphically now. Dilatant fluids are called shear thickening fluids. Why? Let us see. Mu apparent, I am using the symbol mu a. It increases if either tau increase or rate of shear strain du by dy increase. Let us further discuss it. You take a graph. Take some point here corresponding to some value of du by dy. You know, x-axis represent shear strain rate. Now corresponding to this particular point, I say this is some shear stress. I say this as tau 1 du by dy 1. Now I want to join this particular point 1 from origin. Okay, right. You got some slope here. I say this as theta 1. So mathematically, tan theta 1 is equal to opposite side tau 1 by du by dy 1. Now, in case of dilatant fluids, you take some other point here. This I call it as tau 2. On y-axis, I say this as du by dy 2. So I say this as 0.2. Say now I want to take the slope of this point. You see here carefully, this is theta 2. Baba, theta 2 more than theta 1. You already know this slope represents indirectly the viscosity. Of course, here the apparent viscosity. Now I join these 2 points 1 and 2 from the origin here. Please bear with me, I am very poor in drawing. You see the curve? So this is a classical example for graph of dilatant fluid. Some students will have a doubt. Sir, we came to know that viscosity is the slope of this curve, na? They argue like this. Sir, you said 0.1. At 0.1 you draw a tangent. This slope is different. At 0.2 you draw a tangent. This slope is different. You see, this tangent is not parallel to the original line. This tangent is not parallel to this original line. Remember, here the apparent viscosity not represented by the tangent to the point on the curve. It is the slope with respect to origin. See, you might have studied strength of materials, or you will study, or you will study secant modulus. There is one term called secant modulus. So this apparent viscosity is in fact similar to secant modulus. So as you see here, slope is increasing, viscosity increasing, resistance is increasing. I told you, na? Viscosity resistance is increasing, shear thickening. So therefore, dilatant fluids are also called shear thickening fluids. Sir, can you give some example? Examples are many. Starch, maybe rice starch or corn starch. And even have sand, let us say, wet sand. I give a practical example. You go to a beach, assume the sand near the coast is wet. Try to walk on slowly. See, once you walk on the beach, sandy soils, wet sandy soil, when you are walking slowly, the shear strain rate applied is less. Since shear strain rate applied is less, shear resistance is less. So you will see maximum deformation of the sandy soil, and you will sink almost. You will sink. Suppose you jog on that wet sand. You see, the deformations are very less. So meaning is, when you are jogging, the applied rate of shear strain is more. As I told you, na, apparent viscosity increases, either tau or rate of angular strain or rate of shear strain is more. So when you jog, you are applying higher strain rate, that is leading to more viscosity. Therefore, while jogging on a wet sand with high speed, you won't see much sinking of the sandy soils. So that is also a classical example of dilatant fluids. You can have more examples in the materials you can see. Now let us see pseudo-plastic fluids. What are these things? Again, let us go back to the power law. If tau y is equal to 0 and n less than 1, if it is more than 1, dilatant fluids. N less than 1, then it is called pseudo-plastic. Now let us discuss further. Tau is equal to A into du by dy whole power n. I rewrite like this: A into du by dy whole power n minus 1. I'll keep it in bracket. Again, du by dy. Now, this is nothing but mu apparent du by dy. It means here, as usual, mu apparent is equal to A into du by dy power n minus 1. Of course, here n is less than 1. Now these pseudoplastic fluids, they are also called shear thinning fluids. Shear thinning fluids. Now let us discuss why the pseudoplastic fluids are called shear thinning fluids. Now let us see why pseudoplastic fluids are called shear thinning fluids graphically. du by dy tau. So in this type of fluids, what happens? Mu apparent decreases if tau or du by dy increase. Let us see this. Now you take some point 1. So for this point 1, say this is du by dy1. Now this is tau 1. So for this point, let us take slope from origin. Say this as theta 1. So theta 1 corresponds to tau 1 du by dy1. I'll write here. Tan theta 1 is equal to tau 1 by du by dy1. Now you take some other point. Say in this type of fluids, what happens? You take this is point 2. For this point 2, as usual, say this is du by dy2. This is tau 2. Now again try to show the slope of this point with origin. Say this is theta 2. In a similar fashion, if you take some other point, you may get, say, like this. Again, if you join here, sorry, tau 3 du by dy3. Again, connect from origin. Okay, this is a straight line. So this is theta 3. So, as a layman, you can say that theta 3 lesser than theta 2 lesser than theta 1. So this theta is nothing but apparent viscosity. So this apparent viscosity decreasing, resistance is decreasing, shear resistance is decreasing, theta decreasing. Since shear resistance is decreasing, these fluids are called shear thinning fluids. No sir, you draw the curve. Okay, let us draw the curve. I'll take a different color. Join this point. Yes, yes, you see. So this is shear thinning. As I already mentioned, you have to take secant modulus, slope from the origin to any point, not the tangent, slope of the tangent. Okay, so pseudoplastic fluids are also called shear thinning fluids. Now let us see examples for pseudoplastic fluids. The most popular example in several competitive exams of state service commissions, etc. blood. Of course, milk, paper pulp. Of course, here I want to make one submission. If you refer books of several authors, sometimes paper pulp may be shown in some other type of fluid. Don't get confused. In fact, there are some fluids which behave differently in different conditions. Okay, differently in different conditions. So, under certain conditions, I am using the word under certain conditions, paper pulp may behave as pseudoplastic substance. Now I am going to discuss Bingham plastic substances. Again from this power law. Here tau I not 0. Tau I not 0. It is more than 0. And of course, n is equal to 1. So now what I say? Tau is equal to tau I because it is non-zero plus a into du by dy. Now I call this, I rewrite this as tau I plus mu apparent into du by dy. Now let us take an example for this, graphical. So I said yield stress or minimum stress required to start deformation is not 0. Say some point. Now from here n is equal to 1. Since n is equal to 1, it's linear. This is Bingham plastic. Now let us see the example for Bingham plastic. The most popular one is toothpaste. I want to say here it will have a dual behavior. Toothpaste will have a dual behavior. Sir, what is it? You see this graph as usual. Y-axis shear stress. This is shear strain rate. So this is the minimum yield stress. Already I told you. Minimum yield stress. Suppose the applied shear stress is less than this yield stress. What will be the stage of this toothpaste? Here I want to give some additional information. So I want to show you what is the meaning of x-axis. See, for x-axis, y is equal to 0. Y is equal to 0 means shear stress or shear resistance is 0. The fluids which have no resistance, you all know they are nothing but ideal fluids. So x-axis represents ideal fluids. So y-axis, I think all of you know it. Y-axis means x is equal to 0. X is equal to 0 means shear strain rate is 0. Shear strain rate is 0. Rate of shear strain is 0. So such things in fact are called solids. So y-axis is solids. So they may deform, but shear strain may be there, but shear strain rate is zero for solid bodies. Now come to our point of discussion, toothpaste. So as long as the applied shear stress is less than tau aina, suppose nana tau less than this minimum yield stress, toothpaste will behave like solid. Suppose tau more than tau y, as I already mentioned, Bingham plastic. Of course, what is this? Linear, because the power index n is equal to 1. So toothpaste is one solid example for this particular Bingham plastic. There are some more examples you can understand. Now let us see a graphical animation of all types of fluids we discussed till now. So as already discussed, the x-axis represents ideal fluid, the y-axis represents ideal solid. Now you see Newtonian fluid, linear, starting from origin. You see dilatant fluid, we already discussed. Pseudoplastic, blood I told you na, already over. See Bingham plastic, after some minimum yield stress tau y, clear na? Now you see rheopectic, it is time dependent non-Newtonian fluids after some minimum yield stress. You see thixotropic, again after some minimum yield stress, this is the behavior. So I have shown here all types of fluids discussed so far. Okay. Now let us take up time dependent non-Newtonian fluids. Till now we studied time independent non-Newtonian fluids, but now time dependent. In this first, again let us go back to power law. Tau is equal to tau y plus a into du by dy whole power n. Tau y more than 0. If n less than 1, if n less than 1, then it is called thixotropic fluids. I'll draw the curve itself. So tau y more than 0, okay, more than 0. Some initial yield stress is required so that deformation starts. Yeah, like this. So it is something like pseudoplastic after some initial yield stress. Tau y. So now what are some examples, sir? So the most popular example is printer's ink. Some state government exams, an exam they ask this, printer's ink. And of course, lipstick. Lipstick is also generally thixotropic substance. I repeat, sometimes see these fluids may behave in a different manner depending upon different conditions. So under certain conditions, so printer's ink and lipstick are thixotropic substances. Now another time dependent non-Newtonian fluid, rheopectic. I'll show the graph here. Simple, like this. So here also tau y plus a into du by dy whole power n, tau y more than 0, n more than 1. Rheopectic. Of course, the most common example of rheopectic substances is gypsum solutions. Now I want to compare thixotropic and rheopectic fluids, which are time dependent non-Newtonian fluids. I'm going to compare them. So here x-axis I'll take time, y-axis I'll take mu apparent. Now you draw a horizontal line. So if you draw a horizontal line, it is nothing but the behavior of all common fluids. What does it mean, sir? It means viscosity is constant with respect to time. Is time independent for various common fluids, maybe Newtonian fluids, or among non-Newtonian you have some independent fluids we already discussed, like pseudoplastics, dilatant, etc. Now in the case of thixotropic substance, what happens? This is thixotropic. Means for a particular shear stress for a given conditions, as time increases with respect to time, the apparent viscosity decreasing. I already told the example, printers, ink, and lipstick, etc. Coming to rheopectic, this is rheopectic. I give the example gypsum. See, with respect to time, you know, the resistance, shear resistance, which is nothing but viscosity. So the viscosity of gypsum increases with respect to time. So this is a beautiful example to compare the thixotropic and rheopectic substances. Viscoelastic fluids. Viscoelastic fluids. Okay. So generally fluids will undergo deformation on application of shear stress. Suppose this applied shear stress is removed or released, let us assume. Then in case the fluids can regain their shape, the shape is regained, something like elastic. We study in strength of materials. So on release of shear stress or applied stress, if the fluids can regain their shape at least partially, then they are called viscoelastic fluids. Sir, can you give some example? So there are some biological fluids, and of course sometimes in pipes mixtures. What are those mixtures? Mixture of solids and fluid. Assume through pipes mixture of or combination of liquids and solid particles flow. They also behave like viscoelastic fluids. To conclude, I want to bring the difference between ideal fluids versus real fluids, because till now in several cases we might have used the word ideal, real, etc. I want to conclude. So what are ideal fluids or perfect fluids? Ideal fluids are non-viscous, no viscosity, or frictionless. See the word frictionless. It is a single word. Friction, spaceless, no. Frictionless, no friction, no resistance against motion. Some professors call this also as inviscid. Okay, so ideal fluids are non-viscous, frictionless, or inviscid. The second is incompressible, no change in volume. Okay, no change in volume. We assume no surface tension. See, no compressibility, no resistance. Practically, such fluids doesn't exist. Therefore, ideal fluids do not exist in nature. Then why this term has come? Actually, the term ideal fluid was coined, given by mathematicians. Why, sir? To make a complex problem simple in nature. To simplify the calculations, ideal fluid is an imaginary fluid. It doesn't exist practically in nature. Already told you, it doesn't offer shear resistance when fluid is in motion. Now see the velocity distribution. It is almost rectangular velocity distribution. This rectangular was previous question, I don't remember in GATE or IS. Velocity distribution is rectangular. Sir, these characteristics in fact valid for all fluids? Is it valid for liquids and gases? Suppose if you want to apply for gases, you see the second character, incompressible. Whether gases are incompressible? No. So honestly speaking, these are the characteristics related to ideal liquids. In the name of ideal fluid, these are valid for ideal liquids. Then what about ideal or perfect gases? We'll see now. Now let us see what is a perfect gas. A perfect gas is the one which obeys, satisfies perfect gas equation. PV is equal to mRT. P is equal to mass by volume into RT. P is equal to rho RT. So a perfect gas is the one which satisfies perfect gas equation. This is perfect gas equation. Okay, right. Now in this, all of you know, rho is the mass density of fluid. Then what is this? R. Earlier I forgot to tell you, gas constant. This is approximately considered as 287 joule per kg Kelvin. What is T? Absolute temperature in Kelvin. Sir, how do you work out? 273 plus T degree centigrade. So T Kelvin is equal to 273 plus T degree centigrade. So any gas which satisfies the perfect gas equation is called perfect gas. Of course, in GATE civil, it's not that much important, but in various state service commissions, it's very important. One favorite question in various competitive exams: what is the bulk modulus of ideal fluids? So we know bulk modulus is equal to dP by dV by V, of course with minus sign. So ideal fluids
how we have studied in case of liquids? Incompressible. Change in volume is 0. So dV 0, dV by V 0, volumetric strain is 0. So denominator 0, therefore K is equal to infinity. So the bulk modulus of ideal fluids is infinity. Suppose I want coefficient of compressibility. What is coefficient of compressibility? Beta. This is equal to 1 by K. So 1 by K, assume yourself, work out yourself. I don't give the answer. Now I want to correlate with respect to strength of materials. In strength of materials, you have studied the topic Poisson's ratio. So what is Poisson's ratio of incompressible fluids? Incompressible means no change in volume. Which is example? Rubber, ideal, elastic, incompressible material. So for ideal, elastic, incompressible materials like rubber, Poisson's ratio is 0.5. Incompressible means volumetric strain 0. Just for fun, not exactly true. So I can say that the bulk, the Poisson's ratio of ideal fluids is 0.5. Not exactly correct, just I am trying to correlate with strength of materials. Okay. Now real or practical fluids. Practically speaking, all fluids are real fluids because ideal fluids do not exist in nature. Means real fluids have friction. They have friction means they are viscous in nature. So real fluids are viscous in nature. They offer resistance against motion of one layer of fluid over another layer. They are compressible in nature. I told you, all fluids are practically compressible. So all fluids are practically real fluids. Of course, you may say they will have surface tension. Okay, so I gave a brief difference between ideal fluids and real fluids. So number of questions will be appearing in exams on these concepts. Now let us see another theoretical question. Of course, graphical relation of fluids. The following shear stress shear rate relationship was obtained for a fluid. So velocity gradient values are given, shear stress values are given. What is the classification of the fluid? Okay, if you carefully examine, okay, tau versus du by dy, both are having the first coordinate 0 0, means passing through origin. Okay, now you see du by dy, tau ratio 1 by 6, 3 by 8 is equal to 1 by 6, 5 by 30 1 by 6. See the tau by du by dy, or else 6 by 1, 18 by 3, 30 by 5. Constant slope. Anything of constant slope is a straight line. You know, this is nothing but Newtonian fluid. Yeah, other type of fluids we have already discussed. So answer is C. Kinematic viscosity. I use the symbol nu, 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 this is equal to mu by rho. What does it mean? It is the ratio of dynamic viscosity and mass density of the fluid. It is the ratio. Now, I want to work out the dimensional formula of kinematic viscosity. Mu, dynamic viscosity. You know that m by LT. Already have done the derivation. Rho, meter density. Density is equal to mass by volume. Mass by volume. Okay. Now what happens? M cancel. You got L square by T. So the dimensional formula for kinematic viscosity is L square by T. So what does it mean? So L square by T generally meter square per second. Of course, there is one common unit. Generally, kinematic viscosity is expressed in terms of Stokes. Stokes, a great scientist. So what is this Stokes? This is nothing but 1 centimeter square per second. Now suppose what is 1 meter square per second? So 1 meter square per second is equal to 10 to the power of 4 centimeter square per second, or 10 to the power of 4 Stokes. Now, sir, why it is called kinematic viscosity? So earlier we used mu, dynamic viscosity. I want to give a little bit of clarity. Why dynamic? Why kinematic? See, dynamics deals with force. So in fact, dynamic viscosity or viscosity deals with force. Of course, you have also studied the viscosity as Newton second per meter square, where Newton represents force. So the viscosity and dynamic viscosity, which is in fact the property of fluid in motion, I am using the word, the property of the fluid in motion involves the force. Therefore, the viscosity is also called dynamic viscosity. Now coming to this kinematic viscosity, why it is called kinematic? You will come to know in future. Kinematics deals with the motion of a body without reference to the force causing it. What are kinematic parameters? For example, velocity is a kinematic parameter. V is equal to L by T. So no force term. Now come back here. What is this kinematic viscosity unit? L square by T. It has no force unit. Since it has no force unit, it has only kinematic parameters. It is termed as kinematic viscosity. Fine, sir. Sir, we have already discussed dynamic viscosity. Too much, na? Why another parameter, this kinematic viscosity? So my dear students, in fact, dynamic viscosity of gases are very low. Sometimes in the analysis, calculations, very low values are difficult to use in various systems. So dynamic viscosity of gases are very low. So I want to have a considerable value so that my calculations are simplified. You know, kinematic viscosity is in fact very important for gases, because the gases will have reasonably high kinematic viscosities. Okay, since dynamic viscosity of gases are very low, difficult for estimations and calculations,
this kinematic viscosity parameter is introduced. So kinematic viscosity of gases are very high, generally more. Therefore, kinematic viscosity is in fact important for gases. So I will repeat. So kinematic viscosity is the ratio of dynamic viscosity and mass density, and it has the unit of L square by T, meter square per second. In CGS system, the unit is 1 centimeter square per second, which is nothing but 1 stoke. 1 meter square per second is equal to 10 to the power of 4 stokes. Sometimes I may use a unit centistoke. What is centi? 1 by 100th of a stoke. Okay, so this is about definition and units of kinematic viscosity. Now I want to compare for water and air the values of dynamic viscosity and kinematic viscosity. You will see a quite contrary picture. At 20 degrees centigrade, I am considering. For water, the dynamic viscosity at 20 degrees centigrade is approximately 1.005 into 10 to the power of minus 3 Pascal second. At same temperature, for air, it is approximately 1.81 into 10 to the power of minus 5 Pascal second. What does it mean? At 20 degrees centigrade, mu of water is more than that of air. How many times? 50 to 55 times that of dynamic viscosity of air. This is a very popular, famous question in various public sector undertakings. Suppose if you go to 0 degrees centigrade, so at 0 degrees centigrade, the dynamic viscosity of water is approximately equal to 100 times that of air. So this is one analysis. Okay. So in a nutshell, generally being asked question, at room temperatures, dynamic viscosity of water is more than that of dynamic viscosity of air. Now come to kinematic viscosity. Say I am taking 20 degrees centigrade. Approximately the kinematic viscosity of water 1 into 10 to the power of minus 6 meter square per second. Whereas for air, 15 into 10 to the power of minus 6. Sir, kinematic viscosity of air is more than that of water, roughly 15 times. How, sir? Whereas dynamic viscosity of air is less, whereas kinematic viscosity of air is more than that of. What is the logic here? Simple logic, my dear students. So kinematic viscosity is equal to mu by rho, general formula. I told you kinematic viscosity is important for gases. Why? You see here, mu of gases low, density of gases much low, low by much low, more. Simple logic. Viscosity of gases low, density of gases very low. Therefore, kinematic viscosity of gases mathematically more. This is the reason kinematic viscosity of gases are generally more than that of liquids. So in case of water and air, as shown here at 20 degrees centigrade, the kinematic viscosity of air is approximately 15 times. So general question. At room temperature, dynamic viscosity of water is more than that of air, whereas at room temperature, kinematic viscosity of gases or air more than that of water. Now I want to explain the effect of temperature on kinematic viscosity. Actually, there are several empirical formulas for effect of temperature on kinematic viscosity. I don't want to drill into those things. I want to have a simplified analysis. We know kinematic viscosity is equal to
ratio of dynamic viscosity and mass density. And also I focus with respect to gases because kinematic viscosity is important for gases. So I want to go for gases. So for gases, already I told you mu proportional to root T. Okay. And we also know as temperature increases, density decreases, or density in general, density inversely proportional to temperature. Therefore, nu is equal to mu by rho. This is proportional to T power 3 by 2. So, kinematic viscosity directly proportional to T power 3 by 2, where T is absolute temperature. So, you understand this type of analysis to solve any problem in the exams. I will take up now one previous question in gate mechanical so that you really appreciate this particular concept. Now, you take one previous gate question, mechanical question. The kinematic viscosity of air at 20 degrees centigrade is given to be 1.6 into 10 to the power of minus 5 meters square per second. What is its kinematic viscosity at 70 degrees centigrade approximately? This is the question. So, how to answer? So, already I derived that nu proportional to T power 3 by 2. Therefore, nu 1 by nu 2, this is equal to T1 by T2 whole power 3 by 2. So, in our problem, I want kinematic viscosity at 70 degrees centigrade. So, kinematic viscosity at 70 degrees by kinematic viscosity at 20 degrees centigrade is equal to T1. What are T? Absolute temperatures. What is absolute temperature? 273 plus degree centigrade. So, in case of 70 degrees, 273 plus 70 divided by 273 plus 20 whole power 3 by 2. Already we derived. Kinematic viscosity at 20 degrees centigrade given. All other things in gate exam virtual calculator is there. You can calculate. Implies kinematic viscosity at 70 degrees centigrade approximately, if you use virtual calculator, you will get nearly 2.02 into 10 to the power of minus 5 meters square per second. Sir, the value is not there. I told you, this is an approximate analysis. So, if you follow this approximate analysis, what is the nearest option is option A. So, option A. Okay. So, this is the correct answer. It is the ratio of dynamic viscosity and mass